Okay, well, thank you all for coming and welcome to this talk about the PC104 Consortium's latest new standard called OneBank. I'm going to talk to you about PC104 Consortium standards and the latest development called OneBank. And in order to do this conversation, I'm going to wind the clock back in time to about 25 years ago, way back into the previous century, and talk about the origins of PC104 and what we're all about here. So let's talk about what we're here for. What we're all about here really is to solve real-world problems for customers. You know, anybody can take a computer and write software for it, and you can do things like create graphics programmings or Pong games or Monte Carlo calculation of pi and things like that. But the real-life applications for computers are to control and monitor real-world things, real-world situations. So I want to talk about a couple of these applications here. Here's typical. These are actually real applications that Diamond's been involved in. Just to show you what they're all about. And this illustrates what PC104 is about and why we're here. So in this application here, it's a vehicle crash test. In this application, we have a computer is monitoring the crash event, and it has all kinds of sensors in order to monitor the event. So it has analog sensors for acceleration. It has strain gauges to monitor the metal as it deforms. It has wheel sensors. It has other kinds of sensors for the crash test dummies. It has a video camera to watch what's happening. All these different sensors require input to the computer. In the next application here, we have a nuclear plant access control, or any kind of access control system, but in particular in this case was a nuclear system, nuclear power plant. So in this case we have Ethernet for video camera to watch what's happening, and also for networking between all the access points and the main control system. We have, wow, what's happening here? We have a USB or serial interface for fingerprint reader. We have keypads which need to have enter codes and which have a digital I/O input. We have VGA for the user interface and a touch screen so that you can control the system or enter your codes, whatever. And so all of these things, again, are all I/O. The system has to monitor. So back to the very fundamental architecture of a computer looks like this. Basically, you have a processor and you have a bus of some sort. And this bus allows you to connect all kinds of devices, which are all I/O devices. So all of these different things are I/O. They allow the computer to communicate with other computers or with other devices or the real world. And that's really what we're all about here. We're about using computers to control the real world situations, real world applications. So in the original architecture, which I guess was, we all know from the PC world, the x86 world, it all started with this ISA bus, where everything plugged into the ISA bus. And so you would buy a card for each function, a card for video, a card for memory, a card for serial, and so on. And the processor just did the basic processing, and everything was on this one bus. This was how everything worked. Then as time went on, things became evolved, which we'll see in a moment. The truth about real-world applications is that every single one is different. Every customer has their own particular I/O needs. And you don't want to put everything on one board because then the customer is burdened with paying for everything, and they don't want that. They want optimized products. So what you want to do is have some kind of mechanism where the customer can add just the I/O that they need at a reasonable cost and in an easy way. And what this does is it leads to the need for an industry standard and for I/O expansion. So all of these interface standards that you see, what are they all about? They're really all about I/O. They're all about how do you add the I/O that you need to the system. No matter what form factor you see, it's always about how to add the I/O to the system. So there are different kinds of ways of doing this. So one common way is the backplane. Backplanes are great because in the field you can plug boards in, pull boards out, easy to reconfigure the product. Backplanes are very, very configurable and very easy to use, but they're large and very expensive. The next method is a mezzanine system. What a mezzanine means is there's a connector on the board. It's a very low-cost investment by the manufacturer to put a connector on the board and some mounting holes. And then the customer can plug in a board on top of that connector to get the I/O that they need. So it's a great way to give the customer some accessibility to this expansion, to just adding a single I/O card. But it's only one I/O card. You plug the board in and you're done. So in between the two, we have a stackable system or a stacking system. What that means is that you plug a board in, the same kind of low-cost investment by the processor. You have a connector for the expansion, and you have the mounting holes, and you plug a board in, but now the expansion system has been replicated on the top side of the board, so you can keep adding I/O cards on top of the system, and ad infinitum theoretically. You can keep adding up to the limits of the system, but you can add additional I/O cards in the system. So in fact, I was talking with the founder of PC104, the inventor or creator, whatever, earlier today, and he told me that that PC104 in fact started as a mezzanine. That the idea was that they wanted to add a video card onto their single board computers because there were many different video standards in use at the time. And so they didn't want to put all the different video standards on one board, so they tried to add I/O modules in order to allow the customer to decide what the customer wanted to do. So they had a mezzanine connector the customer could plug a board in. Then they hit on the idea of why not let them put other things on there as well, like serial, Ethernet, and so on. Because remember, back then, computers didn't have all this I/O that they have today. They were a basic processor, and everything was an add-on module. So thus was born PC104. So what is PC104 after all? PC104 is a stacking system that allows easy configuration for I/O expansion. And so here's a little more information about PC104. It's basically PC technology. And in fact, this presentation you're watching today is running on a PC104 computer. It's right here, and you can come up and see it at the end of the presentation. It's just a regular desktop PC, just packaged in a way that makes it better optimized for embedded applications. So it's smaller, it's rugged, it's got different kind of expansion system and so on. So it's great for putting into different kinds of applications. Here's a typical PC104 single board computer. This is the board that we're running on today. This is called Atlas, and it's from Diamond Systems. This is using the Atom N2800 processor, which is a standard Intel processor. And it has onboard memory. It has all kinds of standard peripherals. It has Ethernet, serial ports, SATA, USB, LVDS, VGA, all the stuff that you expect to see on a regular desktop computer, just packaged in a different way. Now, the term PC104 applies to a wide range of expansion methods, but all of them are centered around the same physical form factor. They all have the same physical board shape, but some different connectors depending upon the kinds of buses for interfaces for adding on to I/O cards. So here's a typical PC104 system, showing the stacking nature of the system. And for the number of cards here that you see, you can realize this is an older system because back in the days when CPU boards didn't have everything on them, you had to have a lot of I/O cards. So this stack actually has 7 boards in it. Let's see if I can remember what's on here. So going from back to front, the back is a power supply, then there is a CPU board, and then there is a custom I/O card for customer specific. So another great thing about PC104 is customers design their own I/O modules very often for their own particular I/O needs to plug onto the system. Then there's a couple of analog I/O cards, and then there's a relay card, and then finally another signal conditioning module, another custom board. So 2 custom boards and 5 off-the-shelf boards from vendors in this system. And that's the stack by itself. Here you see on the right the actual application. This whole application was mounted inside of a 7-inch diameter body of a vehicle that was flying through the air at 600 miles an hour. This is actually a UAV that was used as a decoy. So the UAV would emit signals that look to enemy radar like a larger warfighter, so that the fighter plane, so that they would basically track it, illuminate it with the radar, try to shoot it down, basically reveal themselves and waste their resources fighting down this, shooting down this very low-cost object in the air. Well, then we could go in and behind them and do whatever. So that's what it was. That was a very successful program. And it all was brought about by PC104. So PC104 is perfect for this kind of application, which is small size vehicles for land, sea, and air. And we see a lot of, in fact, UAVs is one of the largest markets for PC104 today. So this is a little data about PC104. This is the basic, original, classic PC104 form factor. The board is 3.55 by 3.775 inches. It has the ISA bus connector, because remember, this came all from desktops. So it was invented in the late 80s when ISA was the only bus around. So it has the ISA connector on a 104-pin connector, which is where the name comes from. 8 megabytes per second. The connector, 104 pins, has 1.04 square inches in size, and it's roughly $5 in cost for the connector. Here's an example of PC104 SBC, again from Diamond. This is a single board computer with all kinds of I/O. It's got video, it's got memory on board, it's got Ethernet, it's got serial, USB, and it has also an onboard data acquisition circuit. A lot of features on one board. Then, as time went on, technology advanced to PCI bus, much higher bandwidth, much higher data rates. So as the processors and the chipsets that they interface with moved to higher technology, PC104 evolved with them and added PCI to the ecosystem. So what we did was added this new connector at the top of the board to provide PCI bus. We kept the ISA bus in there in order to maintain backwards compatibility, allow people to utilize this existing ecosystem of I/O modules, but added PCI for now high-speed expandability. So PCI connector offers 132 megabytes per second data rate, 120 pins, about 0.74 square inch, and roughly about $6. And these prices I'm showing you are all approximate, and these are all pretty much Diamond's pricing. So you may find different pricing, better pricing. You can benchmark yourself against us and see if you're doing better. But these are roughly the prices that we're paying for that application, for that particular connector. And here's an example of a PC104 Plus SBC. This is Pegasus. This has an LX800 processor. On the top it has the PCI connector, and the bottom has the ISA connector. So same physical form factor, just has an extra connector at the top for the PCI bus. You'll notice here on the left and right these little things that we call wings, little extensions on the sides. This is very common, and we'll talk a little more about that. The reason for that is to give more space on the board because of all the I/O connectors that people need. Okay, so what happens is embedded computing, at least the processor, is kept evolving. They're constantly trying to keep up, constantly trying to add more features, reduce costs, and so on. So these buses that we're talking about are parallel buses, ISA bus, PCI bus. They have a lot of pins. Okay, pins are expensive. Pins require a lot of space in the PCB, a lot of space in the chip, a lot of routing time, a lot of routing effort, a lot of issues. So vendors want to have as few pins as possible for the bus interface and use those pins for something else instead. So one by one, processor manufacturers started to drop these parallel buses and go towards other things. They went to LPC, low pin count, which was a version of ISA bus that used only 7 pins instead of 40 or 50 or 60 or 104. And then they went to PCI Express, which uses 6 pins instead of the same number of PCI pins, roughly 60 or so. So when they dropped those buses, in order to maintain the expansion connectors, we have to add these bridge chips, which convert from one bus into another. So in this case, we go from PCI Express to PCI, and then we go from LPC to ISA. This is very, very common. Probably, the majority of CPU boards you see out there that offer these connectors will have some of these chips on the boards. And these chips are add cost and size. The LPC chip is actually quite large. And so this consumes even more area and adds more cost to the board. So you see that the problem is getting worse and worse because we're trying to adapt new technology to existing architecture. So, and on top of that, what PC104 did was, as PCI became more popular, is we added now PCI Express into the ecosystem as well. So now we have 3 buses, PCI, ISA, and PCI Express. Okay, but we didn't want to use 3 sides of the board for I/O for bus connectors. That's just too much. 2 is already a lot. We want the edges of the boards for I/O connectors. So what they did was we decided to migrate from generation to generation. So we went from ISA to ISA plus PCI. Now we had PCI Express, and we decided we can let go of the legacy ISA connector, and we put the PCI Express connector in the position of the ISA connector. So trying to move forward with the technology, ISA is being dropped by the vendors of the chips, so we could drop it from our form factor, and the new generation will be based on PCI and PCI Express. So now it's a new form factor where the commonality is the PCI connector, but then we have this capability of doing PCI Express for the high-speed interface and to support the new peripheral chips coming out using PCI Express. So the PCI Express connector that we are using is 156 pins, and it also has these 3 blades in the middle for power. Each blade can support something like 8 or more amps of current, so it's a nice way to add additional power capability to the connector. It's about 0.8 square inch, and the cost, however, is very high. It's about $33 for the pair. Remember, you have a connector on the top and the bottom of the board. That pair of connectors is about $33, but it's very high performance. Okay, a recent development is that the PCI Express connector has recently been tested for Gen 2 and Gen 3 compatibility, and in the past, so now we can claim that PCI 104 Express is Gen 3 compatible, which is an excellent thing, so you can put really high performance into the PC104 form factor. So we are at the same level of performance as the much larger backplane systems that you see, but in a much smaller size and lower cost. So this is the connector, and I know it's hard to read it, so I'll just kind of walk through, at least by color, we can see what's on the connector. There are 2 versions of PCIe 104. The original version on the left here, which is now called Type 1, has, on the top, the light blue is PCI Express by 1. There's 4 by 1 links. And then at the very top of the green is USB. There are 2 USB ports. The reddish color is SMB and some control signals. And then all the dark blue in the next 2 sections of the connector are PCI Express by 16. So very high performance. Then, as time went on, we realized that there isn't so much demand for PCI Express by 16, but people want some other expandability as well as some other features. So it became a heterogeneous connector. We added all these different kinds of buses to it. So we took away the PCI Express by 16, and we added PCI Express by 4 and by 8 in the gray-blue there, and we added a SATA here in the middle section, and then LPC here in the bottom. So now we have PCI Express by 1, PCI Express by 4, SATA, LPC, USB, SM bus, all these different expansion methods on one connector. This gives you a lot of variety, a lot of applications, a lot of compatibility with things that you might want to do. And that is called Type 2. Okay, so what's happening? The problem is worsening because now as the vendors of chips started dropping all these parallel buses, they started adding more I/O into the processor. So whereas you used to have to buy an external video chip or an external Ethernet chip or an external serial port chip, all those features are now in the processor. So the processor and the CPU board that people are making with it has more and more I/O on the board. This means you need more and more I/O connectors and I/O circuitry. It's not just the connector, but you have things like Ethernet transformers, serial port transceivers, and so on. So there's additional circuitry you need to go with the I/O. So now you have all this extra I/O and all these extra connectors, and you still need to have these large bus connectors, and you still need to have these translators if you want to have PCI ISA. So the board is getting really, really full, and it's really hard to put everything on the board. So what to do? Just as an aside here, just to give you some context, I wanted to compare what we're doing here with single-board computers to COM modules. In a COM module, none of these problems really exist, because all a COM does is take all the processor features and put them on a bus connector. That's it. And it has a power supply. That's all it does. So all the things about the conditioning, the EMI, the ESD protection, the serial port transceivers, Ethernet magnetics, I/O connectors, all of that is left to the customer. The manufacturer just makes a standardized module, which is, here's Intel or AMD or VIA or whoever, their latest processor. We just take their I/O pins and put them on a connector, and it's up to you to do the rest. That's why they can be small and relatively cost effective. Okay, so it's a great standard for customers, but the customer has the burden of completing the design. So with an SBC, you can just buy the product, plug it in, and you're ready to run. With a COM, you have to do the baseboard design. All these issues of interfaces and ESD and EMI and so on are all left to you to design. So it takes a lot of effort. So a single-board computer, in comparison, is a complete solution, which is really excellent for anybody that is doing relatively low-volume products. Okay, so back to the problem, which is how do we deal with the pressure on the PCB in terms of size to provide all the features that people want and the expandability. So the answer was to come up with a concept that we called OneBank. So OneBank is a connector just like the PCI Express connector that you saw a moment ago, but it's just one of those 3 banks. If you go back to the connector here, you see there are what we call 3 banks. Each of these groups of 52 pins, we call it a bank. Okay, so on the top here, you see those 2 banks are the same. It's the second 2 banks that change, but the first bank is the same in both versions. So we kept that first bank, and that's what we call OneBank. So it's 52 pins plus the 1 blade for power. It's only 3 square inch, so it's much smaller than the previous one, and it's about $16, so it's half the price. That's again for a pair, top and bottom side. And there are 2 versions, and the same for PCIe before. There are 2 versions, with and without the PCI connector at the top of the board. And this, what we call OneBank, was just approved by the consortium and adopted within a week. So it's brand new, and you're the first people to hear about it in public. So we're very proud of this, and we think it'll be very successful. So here's comparison. Here's the PCIe OneBank connectors, the connector pinout compared to the regular full-size 3-bank connector. You can see the top is exactly the same. The top, the first bank's the same, and just these 2 banks have been dropped. And here's the feature comparison, so you see exactly what's available on the connector. You have 2 USB, 1 SMB, and 4 PCIe by 1. So it's enough for almost all applications that we see today. Okay, here's a closer up view so you can see the actual signals. So there are 4 transmit pairs, 4 receive pairs, 4 clock pairs. You have SMB down here, you have USB up there, and you have 2 reserve pins. Okay, so what can you do with OneBank? So here are some examples of I/O modules that you could design or that we might offer. So here is a UART. Okay, the UART is using PCI Express. Again, everything we do is designed around the ecosystem of the chip vendors. So chip vendors are using PCI Express, so we need to have PCI Express because we want to add I/O modules using those chips into our systems. So this is a very popular product. This is a very popular UART used around the world. It's a very standard method of adding serial ports to your design. One PCI Express lane goes to the UART. Now what PCIe does is, because PCI Express is point-to-point, if you want what's called a bus, you want it to be multi-drop, right? So how do you achieve multi-drop when everything is point-to-point? What we do is we have lane shifting. So you always pull the lane you want from the first position on the connector. And then the board will shift the lane. So the lane from lane 2 will become lane 1 for the next board. So the next board will pull lane 1 again. So in that case, every board can plug in no matter where it can be anywhere in the stack, and it always knows that lane 1 will be alive because the board before it shifted the next lane into the lane 1 position. So this lane shifting is the key to implementing serial buses, and it's to be used throughout PCIe 104. So very simple. It's simply the UART and transceivers, and you're done. That's it. Very simple architecture. Here is a dual Ethernet module. So now we're using 2 PCI Express lanes and shifting again, but now we're shifting by 2 instead of by 1. So we're shifting 2 lanes over, and so you can put theoretically 2 of those in a system because you have 2 lanes left over. Okay, here is the way to add a mini card. So you want to add a mini card into your PC104 system. Mini card has PCI Express and USB. Well, in this case, both of them are available, and both of them get shifted over. So again, the next board still has USB and PCI Express available. So you can see it's a very low-cost, simple, easy way to interface peripherals and even other types of mezzanine I/O cards into a PC104 system. Okay, well, how many boards can you fit? How many OneBank boards can you use in a system? If you remember that application I showed you before with the ISA Bus, people were talking about 10 boards, 12 boards, but that was back in the days when single-board computers didn't have all the I/O on them that they have today. So today, the typical application is a little more than 1 board. We did a customer survey, and it looks like the average application uses 1.2 I/O boards. Okay, so let's just call it 1. So that's typically what people do. But you could theoretically have up to 7, because you have 4 PCI Express lanes available. So use 1, pass the rest on. You have 2 USB, so you could have a USB device, just like a USB hub, to take 1 USB, convert it into 4 more, which we've done before. And you could have an SMB device as well. So you could have up to 7 I/O cards in its system, but the typical one is typically 1 to 2. Okay, and here is just a comparison table of the different connectors available, so you can see the sizes and costs and so on that they have. Just reference material. All right. So what are the benefits of OneBank to you, the system designer? The OneBanks are, you don't need bridges because the buses are native to the processor. There's no PCI or ISA requiring a bridge. Everything on there is coming directly from the processor point to point. So there's no issues of adding on additional bridges or using up extra PCB area or complex design or software support. It's just point to point. Reduces the cost and the size compared to the existing connector, which is very, very important because now you have more room for all the I/O on the SBC. In this case, we actually put 3 additional I/O connectors in the space that was freed up by going from 3 banks down to 1 bank. So that's extremely valuable when you're using these chips that are highly integrated. And finally, the connector is backwards compatible with existing single-board computers using PCI Express 104. So that means that if you already have an application using one of these existing single-board computers, you can buy OneBank boards, plug them in, fully confident everything works together. There's no issues with software, physical interference, anything like that. It's all been worked out. It's drop-in replacement, or drop-in compatibility. And so who's making boards? Well, several companies are making some products, and here's a few of them on display today. This is a company, about 3 different companies represented here. There's a CPU board here at the top. There's another CPU board over here. There's a Xilinx Zinc processor board over here. There is a video capture board, serial port board, a USB, 4 USB ports, and up here is a PCIe mini card carrier. In fact, that's 4 mini cards. Well, 4 mini cards, that would use up all the connectors, right? All the 4 PCI Express lanes. Well, actually, no. On this board, there's a switch that converts 1 lane into the 4 needed. So even though it's using 4 PCI Express lanes, they all come together and only require 1 lane on the bus, so it helps conserve resources. So those are some products that are out there today, and we know of other companies that are making them but have not yet announced them. So what we see is already there's a lot of interest by vendors in this new lower cost, smaller size form factor, and we think this will really help to grow PC104 in the future and help to bring PCI Express into the ecosystem. Okay, so that's PCIe 104 OneBank. And now let me tell you just briefly about the PC104 consortium in case you're interested. PC 104 Consortium is been around for about 20 years. We initially started back in 1992 with 12 companies, of which Diamond was one, and we've grown. We're currently around 60 members all around the world that make computers and in this form factor or I/O modules or software or components like connectors or enclosures that create the entire ecosystem for PC 104. And we work together to develop standards just like what I've shown you here today, and to help promote them. And if you are interested in joining, here's some information about membership, different levels of membership, and we'd be glad to talk to you about that.